You are not audible, sir.
Yeah, yeah, hello, yes. Can you hear me?
Yes, now it's fine, sir.
Yeah. So, uh, what is how do we proceed?
You can introduce and start the session, sir.
What is I mean, are there any questions or what should I do?
You are not audible, sir. Sir, there is a one question in Google form.
Ah, okay, okay, I
I have
understand.
pasted it in chat box, sir.
Okay, okay, chat box, right? Chat. Okay, so let me read out the question that is asked. Okay, so this is a question from Maria Spurti, and the question is, how does the partition function act as the bridge between microscopic interactions and macroscopic phase behavior? Okay, so first of all, let me try to pose this question in slightly broader context. Uh, so the question is, why is it the partition function produces, has the information regarding macroscopic phase behavior? So let us understand what is the partition function first. So partition function is a way of counting the number of states accessible to the system weighted by the probability of realization of those states. And the remarkable thing that we find is that temperature times the logarithm of the partition function with a negative sign is the Helmholtz free energy of the system. Now we know that systems kept under certain conditions, like for example, if you keep a system at constant temperature and volume, then the Helmholtz free energy is minimized. The system will, all the other parameters in the system will adjust themselves so that the Helmholtz free energy is minimized. So the partition function looks at the microscopic details of the system and finds a weighted average sum of all the possible states weighted by the probability density, and this is related to the Helmholtz free energy. So the Helmholtz free energy is the phenomenological way of understanding the phase behavior, etc., and the partition function is a microscopic way of counting states, if you wish. So that is how the connection comes up, and this is how the partition function is able to capture the physics of macroscopic phenomena. I hope that answers the question. Okay, there's only one question in the Google form and I have answered it. Okay, are there any other questions?
Hello,
Yes, please.
am I audible?
Yes, yes.
So, are there any examples where two different models describe the same material? I mean, how could we make sure that the phenomena that we want to describe is uniquely described by this particular model that we have constructed?
Okay, that's an excellent question. So the question that's being asked is a model, is there a unique model for any given phenomena?
Yeah,
Can I, yeah. So the answer
yes.
is clearly no. So you will see later in the course that there is a notion of something called as duality, right?
Okay,
So we'll actually construct models that are different models, apparently different models, which will describe the same phenomena.
okay,
Okay, so this is a very common theme in physics, that you can describe the same phenomena using different models. So maybe give you an example, then you will be able to see this more concretely. Okay, so suppose I were to try to understand a certain phenomena, like for example melting of a solid,
yeah,
right? Then what I would say is that I can take the, let's say, the positions of the atoms or and their momenta as the degrees of freedom,
yeah,
and I can try to construct a Hamiltonian based on the nature of the interactions between the particles, etc. So if they are like not ionic particles, like they are neutral particles and they are interacting by van der Waals forces or something, then I would just write something like a Lennard-Jones potential and write this down and try to solve this model to find the melting transition. Okay,
okay,
or some liquid gas transition or something like this, right? Okay. Now, in this context, it is very clear what is the natural model for this, right? The natural model is, we know that we know from variety of experiments that these atoms are interacting with each other and they are changing their configuration when you increase temperature. So they are starting to move around strongly and then they melt and so on. So there is a natural model which describes this, say the melting transition, right?
yeah,
But now, suppose I were to think about some more exotic problem, right? So we will see some examples of this later in the course, but I may have to introduce some notions which you may or may not be familiar. I'm not sure what your background is. So suppose I had something like a gauge theory, like electromagnetism, right?
okay,
So now electromagnetism will produce photons, right? So you can see that there are gapless, photons have a dispersion omega going as c times k, where c is the speed
yeah,
of light and k is like the wave vector. So as you go, k goes to 0, you will see that it becomes gapless in the sense that there will be no energy required to produce
yes,
yeah. Now, the same gapless modes can be realized by a different model, completely different model,
okay,
right? And those models are called dual models, right? So electromagnetism, as you know it, is unfortunately self-dual, so that the other model is also the same model, right? So the electric and magnetic fields will reverse their roles. Okay, but there
okay,
are more exotic forms of electromagnetism called as tensor electromagnetism, which will be dual to dual, meaning the same physics is described by another model, dual to elasticity theory. So for example, if I take a two-dimensional elastic solid that has a theory, right?
okay,
That theory will be dual to a form of electromagnetism called as tensor electromagnetism. Okay, so
okay,
what is the message I'm giving you? The same physics can be described by two very different models. And in many contexts, we are actually, especially in condensed matter physics, the degrees of freedom we use are the natural degrees of freedom that we probe experimentally, right?
okay,
But it could be that the same physics could be described by some completely different set of degrees of freedom by some kind of duality and stuff like Okay,
Okay.
so so the answer to the broader answer to your question is that there is no unique choice of Hamiltonian and system to describe some physics. Most of the time, the Hamiltonian and the degrees of freedom that we choose to describe a certain model are typically motivated by the experiments that provide us the motivation to study these models. Right. For example, the example I gave you of liquid to solid transition of some system, we know what are the degrees of freedom undergoing that transition, etc. So there is a natural model that is suggested from the experiment. But it is not that physics is captured only by that model. It could be captured by other models also.
So do they need to be in the same universality class?
They will be naturally in the same universality class because they are describing the same physics, right?
Okay. Yeah. Yeah.
Yeah.
So in your slides, you also had a problem where uh, there were placates in that 2D Ising model,
Yeah,
and
can you please tell me this which lecture number so that I can pull up the
just
slide
just
and look?
just a minute, just a minute. Yeah. So it's chapter 2, model symmetries and scales.
No, lecture number. There will be a lecture in the
Okay.
bottom of the
Okay.
slide. There
Okay.
will be, yeah.
So it's lecture 4, week 1.
Correct. Lecture 4. It's lecture 4, right? And pulling up lecture 4. Okay. Yeah, there is a question. Yes, there is a question on slide number 13 is what you're asking, right? Is that the
Yeah.
one you're asking?
Yes. Yes.
Yeah, yeah, yeah.
So firstly, that uh, placate index on the coupling constant. So is it a typo, or is it, or will it be
No, no, no,
there?
no, no, no. That is to say that it's not a typo. So
Okay.
maybe if I share my screen, can you see my screen?
Okay. Just a minute.
I'll share my screen. I don't know whether you will be able to see it or not.
Yeah, I'm able to see it.
Okay, good. Then let me let me do some writing for you. Okay. So the idea is, I hope you can see if I write now.
Yeah. 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 It's perfectly visible.
Yeah, good. Okay. Okay. So let me see. I want to move this. How do I move this away? Okay, some small technical problems. Okay, good. All right, good. All right, now I'm ready to get control set. Get rid of that. Okay. All right. So here's the story. Okay. So usually is imagine that I have a square lattice. Okay. So I have a square lattice, and I define the usual Ising model. So what do I do in the usual Ising model? I put I take this and I define, if this is S1 and this is S2, I define some interaction which is minus J times sum S1 S2, right? Or we just
Yeah.
write it just for one of these, right? So S1 S2 like this. Now the idea is that if I do a global symmetry transformation, then this S1 will go to minus S1 and
Yeah.
S2 will go to minus S2, and
Yeah.
this object will remain invariant.
Yeah.
But now you see, so let me ask you a question. So this is what I call J, you see. So I call this
Yeah.
J. So I want to
Yeah.
use, suppose I define 3 spin interactions. Then I have to give a different index, right? I have to give a different name for this, right? Because otherwise you will
Okay.
get
Yeah.
confused with this. So I could
Yes.
call this as J3, S1, S2, S3, like this. So suppose I do this S3. So now let me ask you a question. Will this be invariant under the global spin flip transformation like this? So S3 will
No.
go to minus S3.
No, it will not be, because
It will
I
not be,
mean,
correct? So if I
yeah.
have J3, it will not be invariant, correct? But
Yeah.
now suppose I take these 4 guys, 1, 2, 3, 4 like this. And this is
Yeah.
what we call the placket. You see, that's the placket.
Yeah.
So we say instead of writing J4, we just draw a picture. So that's like J placket.
Yeah.
S1, S2, S3, S4.
Yeah.
But if I now ask how will this remain invariant under the symmetry transformation, it will remain invariant under
Yes.
symmetry transformation. So what is being asked here is to ask is it Ising symmetric, and the answer is it is Ising symmetric.
Yeah.
So then the question here is, if so, why are we not considering it? So should we, because you have this term and you can write terms allowed by symmetry. Why are we not writing this term?
Yeah.
So that's the question asked to you.
Yeah. So my question is, the J placate should be inside the summation sign.
No, okay, that's a question of whether you are imposing translational symmetry or not, right?
Okay.
So if you put J placket inside the summation, that means associated with every placket there is a different J.
Yeah.
But if I had translational symmetry, that is all the plackets are having the same J, then I can take
Okay.
it
Then
outside.
then can be
Yeah.
pulled out. Yeah.
Yeah, but the interesting question to ask is, why are we not considering this term?
Okay. So any hints?
Okay, all right. So it turns out that you can write down this term, but this will turn out to be later you will realize that it will turn out to be what is called as an irrelevant operator, in the sense that it will not affect the universal behavior. You see, the critical exponents, etc., will not be affected by this term. Okay, this is a fairly advanced point, but we will see that later.
So is it
Can you hear me?
because, yeah, so is it because, let's say if we multiply S1 and S2, we get some configuration. So we do it for the entire configuration, we get some value. But if we take, let's say, this expression, the S1, S2, S3, S4, we plug in the values for that configuration, we get the entire same thing.
No, it's not for that reason. See, the idea is that it will change some. You see, okay. So you remember the phenomena, the discussion in the earlier part of in the earlier lectures, right? We showed that there is some critical behavior. So the critical behavior is actually described by a set of critical exponents.
Yeah. Yes.
Those critical exponents turn out to be universal. So, for example, the Ising model and the liquid gas transition will have the same exponents. It even forgets what the degrees. It even forgets what the degrees of freedom are. In one case, it is atoms. In the other case, it's spins. Right?
Yeah.
So the point is, we are not considering this because later in the course we'll show that terms like this will not change the value of the critical exponents.
Okay.
And why they don't change the value of the critical exponents is the puzzle. That is so that's like, why are all these details not being why are they not seen in experiments? In fact, that is the puzzle of critical phenomena. How does universal behavior emerge? How can we get away by not considering this kind of terms?
Okay.
So we'll learn why we are not considering this later. Maybe quite later in the maybe in week 10 or 11 we will learn about that. Okay. So right now, if you have appreciated that this should be allowed in the Hamiltonian because it's Ising symmetric, that is good. And you should there is some little bit of suspense that we will leave unanswered at this stage as to why we are not considering it, and still we will see that we will get the correct physics.
Okay.
Correct physics as far as the critical exponents are concerned, okay, not other quantities. If you have some very specific experimental quantities like some value of magnetization at some particular temperature or something, if you ask questions like that, then if you don't treat these terms, you will not be able to get the correct answer. But if you are asking about the critical exponents, right, the parameters that govern the critical behavior, then my claim is that this will not affect the critical behavior. So there are certain things that this will not affect, and there are other things that this will affect. Okay. The things that such terms affect are called non-universal quantities, and there are universal quantities which are not affected by terms like this.
Okay.
Is that, yeah, okay.
So are there any examples of non-universal quantities?
Yeah, so for example, if you take, if I have a first order transition, for example, so there is a latent heat, so that
Yeah.
latent heat is not universal. Okay, so suppose I ask you what is the magnetization of a system at some temperature, that answer is not universal. The magnetization as a function of temp at a particular temperature will not be the same for all materials.
Okay.
So these are all not universal quantities. But if you now, so maybe I will just pull up my the earlier slides. I hope you can see what so suppose I pull up
Yeah.
the first lecture.
Yeah.
So the interesting thing is that if you sort of view this, instead of looking at the temperature itself, you define something called a reduced temperature, little t.
Yeah.
And define it like this, T minus Tc, then you will see that these things will have this universal character. You will find that this M diverges or M has a critical behavior. It's a beta, specific heat diverges in this fashion, susceptibility diverges in this fashion. So the non-universal quantities here are the C beta. This C beta plus and C beta minus will not be the same for all materials. The ratio of those, that is C beta plus divided by C beta minus, they will be universal.
Okay.
Alpha, beta, gamma critical exponents will be universal. Okay, so these are universal quantities, namely the critical exponents and what are called amplitude ratios, not the amplitudes themselves. The amplitude themselves are not universal.
Okay.
Yeah. So why that is the case, etc., is what we are trying to understand in this course. Where does the universality come from? Why is it that, so you see, so it's quite remarkable, right? So if these things are universal, the system seems to forget what it is made of.
Yeah.
That is exactly so that is how, we saw that there is some description of all solids, right? So in this sense, right? So we said that all solids can be described by this dimensionless equation. Gamma is tau tilde.
Yes.
So something like that. So you get this kind of universal quantities out. And so examples of non-universal quantities are this parameter called C beta plus and C beta minus. That these constant numbers will depend on what material you have, what system you have, etc. But the ratio, the C beta plus by C beta minus, or C alpha plus by C alpha minus, or C gamma plus by C gamma minus, they will not depend on what system is realizing this phase transition.
Okay, so as I understand, different systems that belong to the same universality class have some universal properties and also some non-universal properties that are specific to the...
Exactly correct. Exactly correct. That is absolutely correct, yes.
Okay, so the terms that we write in the Hamiltonian are, by imposing symmetries, right?
Yes, correct.
Okay, so how do we know, let's say if a term satisfies a symmetry, then how do we know that whether we should add it or not?
Excellent question. Right, that's exactly the question, right? Okay. So let me give you a practical answer, and then of course you'll realize as we go in the course that answering this question is the key point, right? Okay. So the practical answer, it comes from experience, right? Okay. Right. So you have to know what are the terms that to keep and not to keep. The more serious formal answer to this will come when we study something called as renormalization group, right? So that will be like at the very end of the course. We will write down a general field theory keeping all possible terms. Okay. And then we will try to study certain phenomena near some critical point. And then the theory itself will tell you which are the important terms and which are not the important terms. So that is why I was saying that if so, why are we not considering this? The answer to this question will become evident only at the latter part of the course, when we look at these terms and study what are called their dimensions. Okay, so this, if you have not seen this before, of course it will not make any sense to you. What do you mean by dimensions? But later at the end of this course, you will know what I mean by dimensions as well. So if you look at what are the scaling dimensions of these objects, these terms that we are keeping, then you will see which are the ones that are called the important terms, and there is more technical terms like relevant and irrelevant and all for those. So for example, this term will become an irrelevant term near the Ising phase transition. So in the sense that it will not have any effect on the critical properties. It can have effects only on non-universal properties. So in principle, you have to, if you in principle, of course, if you start with a symmetry, you have to write out all terms that are allowed by symmetry. And the remarkable thing is that even if we are not able to write down, even if we don't write down all terms allowed by symmetry, we can still predict the critical exponents, because it turns out that only a few of them are important to determine the critical exponents. Understanding why that is the reason, what is the reason behind this is the crux of critical phenomena, right? And it is precisely asking the question, how does universality emerge and all of that stuff. Okay, so I hope you realize that I haven't actually given you a concrete answer to decide whether a term should be kept or not. And my answer is, you will learn which terms to keep and which terms not to keep at the very end of the course.
Okay. So, but you told about writing all possible terms and then checking whether they're relevant or not. So, how do we know that we have exhausted all possible terms?
Oh, that you can just, that's a simple problem in group theory. So the idea is that, you take, so you have these fields, right? So here there are these spins. So you can write out all possible, like, so 2 spin interactions, 3 spin interactions, 4 spin interactions. You can write out all of these. And then you can do just analysis of the symmetry. So you can see, just apply the symmetry and see if it is invariant. If it is invariant, you keep it. So you can do this systematically. So you can write out, so there is a formal way of doing it. But the remarkable point is, it's not necessary to do it if your goal is to find the universal properties.
Okay.
Yeah.
So, the Ising model, if we, let's say, increase the number of neighbors.
So can you give me like a concrete example of how would you increase the number of neighbors?
So, nearest, next nearest, and so on.
So that means that you don't want this to be in the nearest neighbor. You want it to be something like this, right? So you want to be first neighbor, next neighbor, and so on, right?
Yeah.
Yeah.
So, I mean.
So question is, how many neighbors do you need to keep? That's your question.
Yes. Yeah.
All right. So I will not give you proof of my statements. They will become evident later in the course. Okay. So first is, let's assume that yes, you can have multiple neighbor interactions. Let's assume that all of them are ferromagnetic. Okay. Because if it is not, then if there is some anti-ferromagnetic interactions here and all, then some complications can arise. Okay. Let's just for simplicity assume that all the interactions are ferromagnetic. Okay.
Yeah.
So all these J's are positive, let's say. Then later in the course you will be able to see that the higher neighbor interactions are not important. They will turn out to be irrelevant.
Okay.
So I can sort of very crudely tell you why that's the case. So roughly speaking, very crudely speaking, the next neighbor interaction can be thought of as like some kind of gradient term. So that is like some, you're taking the difference between objects at two neighboring lattices. So when you look at, suppose you look at interactions between further neighbors, that will be like looking at something like a higher gradient. So we'll see that the more gradients that are there, they will become less important. That's what we'll see later in the course.
Okay.
Yeah. I will check if there are other questions.
So one more question.
Yes, please. Yeah.
Yeah, you described the mechanism by which we do symmetry breaking.
I didn't quite follow what you said. What do I mean by described a mechanism?
I mean, first we take the thermodynamic limit, then we take h tending to 0.
Yeah, we keep a symmetry breaking field on.
Yeah.
First take the thermodynamic limit, and then we set the symmetry breaking field to 0.
Okay, so you told that by doing this, it won't be able to sample to the other.
Correct, exactly.
Yeah,
correct.
So is it in the Monte Carlo sense? I mean, so when we do let's say Monte Carlo of the 2D Ising model, we change the configuration, then we determine the probability if we throw a random number.
Right.
So I mean,
it's certainly true in the Monte Carlo sense, but what I mean more by that is, see, when you suppose you keep a symmetry breaking field on and you take the thermodynamic limit, so and you, let's say you go to very low temperatures, etc., right?
Yeah.
Then you will see that as in the Ising model, if your symmetry breaking field was in the positive direction, then all the spins will point in the positive direction, right? And now you have taken the thermodynamic limit. Now, what this means is that this equal a priori probability postulate will tell you that, if the upspins and downspins have equal probability, that will no longer hold, because if the system is all in the upspin state, there is no way to suddenly flip all of them to the all downspin state. It's exponentially small likelihood that it can flip to the other state. So in the sense that there is an ergodicity breaking, right? So symmetry breaking is associated with ergodicity breaking. Ergodicity, remember the basic postulate of statistical mechanics that all states with same energy are equally likely. That is no longer true when you have symmetry breaking, because you see, I brought all the spins to the up state, so they cannot, the barriers to go to make it all downspin state are so high, and that all of them will simultaneously flip down is exponentially small. You see that,
yeah.
right? And therefore, there is like a barrier to sample the other equal energy state, which is all downspin. It is in that sense that I say that it cannot sample the other one. So it's a way of saying, I didn't want to use the more fancy term called ergodicity breaking, but it is an example of ergodicity breaking.
So, are all these concepts also valid in the quantum case?
So I will say my quick answer to that question will be broadly yes,
Okay.
but they have to be dealt with correctly incorporating quantum mechanics. The answer is broadly yes.
Okay.
Okay, since there are no more questions, we'll conclude the session now. Thank you to all the participants.
Yeah, thank you.